Okay, hello everyone. Welcome to this NetPlays event. And today we have Dr. Matthews Walensky from the Los Alamos National Laboratory, USA, to give a talk today here. And he will talk about statistical inference, learning, and optimization for dynamics on networks. So time is yours, please.
Thanks. Mateusz Walensky. My presentation is built into two parts. Probably the first one is a bit too long. The second one probably a bit too short, but hopefully we'll manage to work with that. So what I wanted to say today is mostly this statistical inference and learning problem for dynamics on networks, which I think is a very important subject, especially when working with data. But at the same time, I feel like not a lot have been done, especially in the part of taking into account problems that we often have with the data. So the data is never perfect. Actually, the data is pretty bad most of the times. And I will try to address some issues and potential solutions for different problems we can have with the data, like lacking information, noise, and so on and so forth. This will be a very general talk. I won't focus on technicalities, but I'll be happy to discuss them later on. And if you're interested, you have some extra questions afterwards, feel free to contact me, or if you have some ideas. Also, I don't see the chat, but feel free to just interrupt me anytime. I don't have problems with that. Actually, it's probably better if something is missing or you have some questions to actually ask it straight away, and I'll be happy to try to answer them. So first, I'm assuming everyone here is an expert on networks, judging by the title. But just a quick comment on the model, so all the results that I will show today will be for one particular model. However, the whole approach and all the tools are easily generalizable to a quite big family of models. And I will also comment on what that family is shortly. The reason I choose one model as a test case is that for this particular model, all the equations are very simple. It just makes it easier to understand and to get the intuition how it all works. And this is a pretty well-known model, which is in the, let's say, computer science community. It's called the independent cascade model. Let me just turn on the time so I'm not talking too long. So in computer science community, it's called the independent cascade model, but it's also actually in the, let's say, epidemiological community known as SIR, more precisely a special case of SIR. So we have susceptible, we have infected, we have recovered, and we have some probabilities of infection, right? So like if one node is infected, then it can infect its neighbors with certain probability here, alpha ij. It can be different for different pairs. So here we'll talk about a general case where those probabilities can be different. But the special case, what I meant by special case is that here the probability of getting recovered is equal to 1. So every time you get infected, you get recovered immediately on the next step. Okay, this is also often used actually even in the epidemic spreading literature, because for the same reason, it simplifies a lot and it makes it easier if you want to show something analytically or just make the computation simple. But as I said, like all that I will show today can easily be generalized, for example, to a general SIR model. So just to give you an example, but probably everyone already knows, but just to give you an example. So imagine you have a network, there's some initial conditions, let's say a single initial node. I mean, there might be different initial conditions, but let's say that's the one. So it has like 4 neighbors. The process is stochastic. So let's say it infects only 2. It immediately gets recovered in the next step. And then the 2 can infect their neighbors also randomly. They immediately get recovered and so on and so forth until the basically until the dynamics completely stops, right? Everyone is either recovered or susceptible. So this is the independent cascade model, and all of the simulations that I will show, the results of those simulations or the procedures will be for that model. But again, this can be generalized. So now, one of the main points, actually, I think that's actually the main point, inference for this kind of problem. So when we observe spreading, what do we really want to infer? What's an interesting thing that we want to know? Let's say we have let's say I give you a model, I give you the network, I give you all the parameters, I give you the initial condition, and what is the question that you might ask? So the most typical question that people ask in the literature is, what is the expected outcome of this spreading, right? So like it starts here. What's the probability that it will spread like on the whole network? What is the expected number of infected nodes at the end? In our case, recovered, but affected, let's say, by the spreading at some final time. Or maybe what is the expected state of the network at some finite time? What will happen after like 5 steps of the simulation, most likely? And this is often referred to as the influence function, which means what is the expected number of infected, or in our case, recovered cases. And this could be described using marginal probabilities. So if we would be able to compute the marginal probabilities for each node, so let's say we have node I, and I want to say, what is the probability that node I at time t got infected, or it got infected in the past? So then we can use those marginals to actually compute this expected values. But computing marginals in general is actually difficult. It's a numerically, numerically it's difficult. It's a hard task numerically. So one of the things that that people do if they want to compute marginals is using a technique which is known in statistical physics as cavity method, or in computer science as belief propagation. And I will talk about a specific case of this kind of technique, which is called dynamic message passing. I will go back to this belief propagation in a moment, but first let me tell you a few words of what I mean by dynamic message passing. So actually, dynamic message passing was known before it was even connected to belief propagation, because it's pretty intuitive. So what do we want to compute? Here we will try to compute the probability of node I being activated or infected at time t or before. So this is our marginal probability for node I, which has several connections. So in general, now we're talking about the general case. This can be written as in the first equation. So it's just basically 1 minus the probability it was not infected at the initial state times qi, which is the probability that it was infected by its neighbors, in short. Now, this probability is actually difficult to compute. So in dynamic message passing, we introduce messages. Okay, so we want to compute this q by using messages. And message from j to I is basically, again, a marginal probability, the same as pi. The only difference is that this probability assumes that the spreading occurred on the network where we just pick node I and we just move it out of the network. So it's an auxiliary graph without node I, okay? And if that's the case, then we can actually write exactly the same equation for messages. The only thing that we need to do is we need to take out this node I now, right? Just from the definition of the message. And now we can see that this is a closed form equation, and we can actually compute everything from it. But you probably already see that there's a problem here, right? Because for it to work, we would need to assume that this part here, if we compute J3 here, that this part here is actually independent on J3. Otherwise, only taking out I is not enough, because the probability can propagate along the loops. So, and this is where we go back to the belief propagation, which is a technique which allows you to compute those marginal probabilities if your distribution is as a factor graph is basically a tree. So in our case, if we go back to the spreading case, it means that these equations are exact if the spreading occurs on a tree. Okay, then those equations are exact. Now, what happens if we introduce loops? When we introduce loops, this is only an upper bound. However, what people already observe while working on belief propagation is that often this upper bound is very close to the exact solution. In some cases, actually, is the best known algorithm to compute those marginals. So if our networks are sparse or so-called tree-like, which an example would be an Erdős-Renyi graph, then this is a very, very precise approximation of the marginal probabilities. So again, I don't want to go to details. It's just that, so the intuition is that we have a method here to compute marginal probabilities, and the method is exact on trees, but it's a very good approximation in general, specifically for sparse graphs, also for very dense graphs, but that's maybe a different story. And this all comes from the fact, so here we only I only said like a couple of words how like an intuition behind those equations, but they can actually be derived point by point from general belief propagation equations. And there are more details are in this paper from 2015 from Andrei Lokov, with whom I collaborate, and all of this work was actually done in collaboration with him. And so because they are derived directly from belief propagation, they also possess all the characteristics of belief propagation, which is, as I already said, like exact on trees, a very good approximation on sparse graphs. Now, one advantage from the belief propagation is that belief propagation is requires you to find a fixed point of these equations, okay? Which may not always happen. Sometimes you may just diverge some. However, DMP, in a sense, gives you equations that are there's no randomness here. You give it an initial condition, and it just computes the marginals. And this comes from the fact that there's a strong simplification here. And this is maybe one of the main assumptions. The simplification is that we assume that this dynamic process on this network is actually a unidirectional process. So we assume that our underlying model is unidirectional. Now, what does it mean unidirectional? It means that if node is in a certain state and then goes to a second state, like in our case, it was susceptible, it goes to infected, it cannot go back. Okay, so all of the processes of the type of SIR, SI, and many other can actually be, you can actually use this approach with those models. But if you have a reversible dynamics, then it becomes a bit more complicated. You can still do something, which I will not discuss today, but it becomes a bit more trickier. So the family of models that I mentioned at the beginning is the family of unidirectional model, which is still a big family, and which is still a lot of models that people actually use for epidemic spreading. Like for example, all of the SIR type models are part of this family. So this is maybe a bit of technical thing, but what is important here to remember is that we have this inference method, which is not exact, obviously, which is perfect on trees, very good for sparse graphs, and which is deterministic in the sense that you give it an initial condition, and I can compute you obviously all the parameters, and I can compute you all the marginals for the whole network, which is very, very useful. And which is also very useful if you're interested in the influence function, right? Because then you can just sum the marginals and you immediately know the answer. It's very simple. And also the equations are linear in the number of edges and in the time that you want to compute the marginals. So this is very fast. It's extremely fast, actually, to compute it in comparison to, for example, Monte Carlo, which I will comment on in a few minutes. Now, to give you a little taste of whether it actually works. So obviously, we're not interested in trees, at least not too often. Typically, the networks that we look at are real networks which have loops, which have high degrees, all sorts of heterogeneity that you can think of. They have a lot of local clustering coefficients, high local clustering coefficients, and so on and so forth. Nevertheless, if you take, for example, here, quite popular network of airports in the US, which I think this particular network was used in many, many papers related to network science. And you just use, as I said, like IC model, for example, then this plot shows you how good is your approximation of the marginal probability. So here on the x-axis, we have the DMP prediction of the marginals at some point. And this is the prediction of the marginals coming from the Monte Carlo simulation. So let's say this is the ground truth marginal probabilities. And obviously, the closer you are to the diagonal here, the better your prediction. And as you can see, even for these networks with many loops, the prediction is very, very, very good. Okay, now, so coming back to the question that I kind of already answered. Why not just use Monte Carlo? Why not just use simulation, right? I mean, you can always do it, and you don't have to worry about trees, you don't have to worry about loops and so on. Well, the main thing that will come very handy in the next part is that DMP has basically the complexity of a single Monte Carlo run. This comes from the fact that, as I said before, it's linear in the number of edges, linear in time. So basically, if you want to have a precise marginal estimation from Monte Carlo, you, for example, may need to do like 1,000 or even 1 million runs for a single, let's say, initial condition and the set of parameters to get it from Monte Carlo. Now, DMP will give it to you in just like a single instance, like a single run. So then you can easily test different scenarios, even hundreds, thousands of scenarios, and it will be much, much cheaper than using Monte Carlo. So this is one thing. But this leads us to the second part, which is learning. So why would that be important in learning? So in learning, often, if you want to learn some parameters of the model, you need to do the inference to compute the likelihood, for example, multiple times. Let's say you're doing a gradient descent. So at each step of this gradient descent, you basically need to recompute your likelihood in a way. So if you would use Monte Carlo, you would need to do those, like, let's say 1,000, 10,000, 100,000 simulations at each step. So the general idea of learning is basically, I give you data and you want to learn the model, right? So in our case, the data is the observed dynamics, the spreading, probably multiple spreadings. And the model is defined by the spreading parameters. So for this IC model, it's simple because there are just the spreading parameters at each edge, right? So we want to find all the alpha ij's. Right, so basically that's the problem. You observe the spreading on the network and you want to find all the original parameters. You assume that you don't know. And now the data, as I said, it's spreading, but actually, if you have all of those alpha ij parameters that might be different for different edges, you probably need not just a single instance of spreading, but multiple instances of spreading. So you have, let's say you have, let's call a single instance a cascade. So you need so your data is basically a number of those cascades, which may start at the same initial condition, but may have different initial condition, but are assumed to have the same underlying model. So yeah, this could be written as this set of activation times in this case. So first, the simplest setting is assuming full information, which is never the case. This is a completely unrealistic case, but let's let's try to tackle all the possible situations. First, we have full information. So by full information, I mean that if we have a cascade, we observe the dynamics on all of the nodes. We know the network precisely. We know what's the state of each node at each time step. And of course, we have number of those cascades. Now, this is simple. I throw some equations at you here, but it's not really important. You don't have to really read them. It's just for the sake of putting them there. The reason why it's simple is that in this case, you can just write the maximum likelihood. You just write the maximum likelihood and then use your favorite optimization tool, or you can just write your own gradient descent algorithm and just find the best alphas according to this likelihoods, which obviously depends on the cascade. Maybe one thing that I will highlight here, because it might be useful later, is that basically in this approach, what you're doing is you're minimizing the chiral divergence between the model parameters and between the model and the empirical probabilities that you get from the cascades. So chiral divergence is it's not a true distance. Probably all of you know about it, but it's kind of distance if you compare two probability distributions. Now, the problem is that in reality, you very rarely observe everything. So, for example, one of the problems is that, like, there was COVID, right? We have plenty of data from different countries. We could, for example, try to create a network of cities or of countries, or depending on the granularity of the data, we can like build this whole network. But in reality, it's never the case that the quality of data is the same. And often some parts of the world may just not report the data, but they still exist and they are still important part of this dynamics. And the problem with that is that in this like network setting, if I would just pick some nodes and say that I don't observe them, so I don't know what's going on there. I don't know whether they were infected or not, at what time they were infected. I just don't know anything about it. I just know the other guys. And I even know the network, but even the sole problem of not knowing part of the dynamics of part of the nodes leads you to a numerical difficulty when you want to use the maximum likelihood, because basically in this case a maximum likelihood becomes exponential. This approach becomes exponential in the number of hidden nodes. So basically, if there is like some percentage of the network is unknown and the network is big, and this is typically the case that we're interested in, big networks, then it becomes numerically intractable. So what can you do in this case? So our approach is, instead of trying to compute this whole likelihood, we focus on the marginals, right? I already discussed this cool inference method that we have that is able to compute the marginals, which is useful to compute the influence function, but it will also be useful here because it will have the same complexity independent on the number of hidden nodes, and each marginal would actually keep the information in a way, the information from the whole network. So instead of computing the likelihood, we'll just compute the marginals. And then we'll do the same. So now our likelihood is, our objective is slightly different. Now we have this sum of like log marginals, but then our minimization problem is actually very similar because we, again, are trying to minimize the chiral divergence between the model and empirical marginals. Okay, so what do we do then? Then we have to use some optimization scheme. I don't want to go to details, but I want to comment on that because what we did is we basically used this like Lagrangian equations approach. So we use Lagrange equations in order to compute the gradient, and then basically we just loop until convergence. But what is this? Why is this important? The important part is that like the reason why we use Lagrange equations is that in this case, we use the DMP as constraints, which makes the Lagrange equations basically a dual equation to the dynamic message passing equations. And the one important takeout from this is that this makes this whole computation of Lagrange equations the same complexity as the DMP. So because of using these Lagrange equations, we keep this linearity in the number of edges and the time span of the dynamics, which makes this algorithm extremely fast. And this was important for us because from the beginning, the assumption was that we want to use it for large networks, right? Because this is the interesting part. You want to have large networks. If you have just small networks, then you can always use the maximum likelihood. It will be extremely slow, but you can still do it even in the unobserved regime. Okay, so maybe let's see some results. So first, the trivial case, which is a regular tree. Here, our inference method will be exact. So we expect very, very good results, and this is what we get. You can see that even if the 25% of the network is unobserved, the result is not much worse than in full observability case, which is very good. But this is kind of what we expected. This is also not very interesting because in reality, there will be loops for sure. So, but maybe let's look at it and also see that we are actually even very good in recovering the parts that are connected to the hidden nodes. So the red crosses are the edges that are connected to the hidden nodes, and the blue ones are connected only to the observed ones. So obviously the blue ones are on the diagonal, which means we have a almost perfect reconstruction. Just remember that now we are not talking about marginals, we're talking about the parameters. So these are this is the true parameter and the parameters we got from our learning procedure. And you can see that even the red ones are highly correlated with the original solutions, which is good, which is what we hope to achieve. But even if we go to a more challenging case and start adding loops, here's an example of a pre-regular graph, but I will actually point to some literature of ours, and you can see that for many different networks like scale-free networks, Ehlers-Danlos networks, and in real-world networks, you get a very good results. But here you can see that the gap between the observed part and the part in the unobserved regime actually is bigger than for trees, which is expected. I mean, the loops makes it more difficult for the algorithms, for the algorithm to give you the correct outcome, but it's still very good. Like the error is really, if you have enough data, the error is very low. But I will comment on the loops in the second part of our discussion, hopefully. Now, okay, so we had unobserved nodes, but sometimes there's the problem of unobserved times. So like there was a certain period of time where you, for example, there was no reporting, or for some reason we just didn't care about the infections, and then we started reporting later on, or we have like multiple holes in our dynamics. So here we observe the whole network, we observe all the nodes, but only at certain time points. And it turns out that in this case, our method actually works extremely well. So even if you observe only the initial case and the final case, which is this last 66% here, you get almost a perfect solution. But you have to take into account, I mean, you have to use this knowledge that you have those missing times. Because if you just like straightforwardly apply the algorithm with those missing time steps, then I mean, you still get something good. But if you do this time correction, which this time correction is basically saying, okay, so I know, I don't know where was exactly the infection for certain nodes, but I know they were recovered or infected later on. So I know that this infection had to take place in some of the period that was unobserved. Then the recovery is almost perfect. And now a more challenging case. So now we assume that part of the network is unobserved, some of the nodes is unobserved, but also even the observed part is subject to noise. So it's often the case that, like, I don't know, you do some sampling, but you do the sampling on Friday, and then the result is on Monday, right? So there's a certain there's a certain noise on the time steps that you have in your data, and it's often very difficult to actually deal with it. But if you have some knowledge about this, the distribution of this noise, you can actually still apply our methods. And if you use this correction, again, you can get very, very good, precise results, even in the regime where like 25% of the network is unobserved. So here is a little comparison because again, you can just straightforwardly use the original algorithm and you get some result that somehow correlates, but it's not very good. But if you include this information about this noise and time steps, you can actually get a very, very, very good results, even if you have loops and even if you have unobserved network. And now the most difficult setting, I would say, is when you have unobserved part of the network, uncertainty on times, and then on top of that, you don't even know the network. So obviously, in this case, there's space for some certain degeneracies, but even so, we can still use our network and get some really good results. And here I will use an example of a real network, everyone's favorite, the Zakari Karate Club, also because it's not so big, so it will be easy to do all the numerical tests. And we assume that it has all of these problems. So we assume that it's like part of it is unobserved, there's uncertainty on the observed part, and I don't know actually the network. And it turns out that even in this very, very difficult regime, we can, first of all, reconstruct the network, and second of all, find the parameters. So here, this part here is just the error on the parameters, the average error. So basically, the closer to zero, the better. And this part here is, we use this like ROC curve measure. So this is like the ROC curve area to check whether our reconstruction, like we don't care about the alphas, but whether our reconstruction based on our algorithm is actually successful. And so the closer it is to one, the more successful it is. So even in this real network, which has a lot of loops and all of the problems that I showed, we are still able to reasonably reconstruct the network even in a 25% unobserved regime. So this is really nice. And okay, I think I'm actually already, oh no, I'm pretty good. Okay, that's good. Oh no, because we also have discussion, sorry. But yeah, so I ran through it a bit quickly, but I'll be happy to answer any questions. And here's some literature. This last paper actually needs to be thrown in archive very soon, and it will be. But the paper itself is ready. And this is our main work that you might find interesting, and some previous works that is also using this dynamic message passing. Especially this first one is interesting because it shows how to derive those equations from belief propagation. And at the end, this is like my GitHub repo in Julia, which has all of this stuff that I discussed today. So the DMP is coded there, even not only for IC, but also for SI, SIR, and all sorts of cool stuff on using DMP for spreading. So yeah, so this is the end of my first part. There's also the second part, but I guess we can maybe have some discussions, or if you have some questions, or maybe you just want to go straight to the second part. I don't see the chat, by the way, so if there's something in the chat.
I think we can like finish the first part by like discussion first, and then we move to the second part. Okay.
Awesome.
Thank you very much for this very interesting talk. I do like this work, and I mean kind of the elegance in the theoretical side, but also the strong motivation from the realistic scenarios. I like it very much. So any questions from the audience?
I know it was a lot to parse. Sorry for that, but I hope there was some at least message that was sent.
Any questions? Well, first of all, I have several questions, if I may.
Sure.
So the first one is when you say this, if the network structure is incomplete, right? You don't perfectly know the network structure. How do you do the reconstruction of the network?
Yeah, so that's a good question. So if you have no knowledge of the network, that's the most difficult case. And this definitely raises some degeneracy if you introduce unknown, unobserved nodes, right? Mm-hmm. But still what you can do is you assume that there's a full network. And then what you do is you basically run the algorithm, trying to find all the alphas.
Right.
And then you do thresholding over the found alphas. So this the problem with this is that this increases the complexity, but it's still n squared, so it's not bad. Now, if you would know the whole dynamics, then you don't even need to use the MP. You can just use the maximum likelihood and do exactly the same. And then the positive thing about using maximum likelihood in this particular case is that you can do it locally. So you can do it locally for all the nodes independently. And so you can easily, if you want to improve your the numerical speed, you can just easily, well, you can run it independently, right? So for each node. So if you have like 10 cores, you can run it independently on 10 cores and so on and so forth. So does that answer your question?
Yeah. Thank you. And I have
basically what you try to do is you try to recover the parameters for the full network and then threshold the values that are small. And this works really nicely. And I will actually comment on that in the second part. How do we, that's why I didn't talk about it too much now, because in the second part, there's a whole story how we actually came to notice that it works, because it's not so obvious that it works actually. If you think about it, it's not so obvious that it will work, at least in the unobserved regime part.
Okay, so when you say full network, you mean the fully connected case?
Yes, I mean fully
connected.
Okay,
so.
But this is the worst case. Sometimes
Yeah,
you know something, right? Sometimes you can assume that there's some network, but just a subgraph of this network actually is in the, let's say, spreading process. Then you do the same, but you don't need to use the full graph, but this like bigger graph. And then this looks like, oh, this works like a chart. Then it works extremely well. It's really, it's fast, and it's also very, very, very good. The error is very small, which I will also show in the second part.
Okay, cool. I have a second question, not so closely related to this work. So it's like when you sometimes you have the missing information, but you can still almost have a perfect inference of the dynamic, which means that these marginals are strongly correlated, which means if you only have part of the observation, you can still fully recover the whole picture, right?
Yes.
Is there any kind of a theoretical argument or a threshold, like if the missing information, the pieces of missing information is I mean, too less information known that we cannot recover things?
Yeah, that's a very good question. So there are some theoretical limits in general on BP that shows you there is actually a very nice work done not on the spreading but on the community detection part. Okay. There is a nice relation there because it also uses often belief propagation techniques to show it. Here I don't have a specific analytical like a number to show you. I don't have an equation. Maybe it's possible to do it, but what we did, and it's actually in the last paper, is that we basically just drew this heat map showing like the dependence on the number of unobserved and the quality of the recovery. So it's not like, it doesn't seem like there's a phase transition, or at least the phase transition is not
it's continuous.
You really need, yeah, in a way, right? But obviously the quality gets lower and lower and lower. So it's if there's a phase transition, it's continuous, definitely.
Oh, okay.
But possibly also there's no phase transition; it just goes to zero as you achieve 100%. But yeah, and this heat map can give you some, let's say, intuition on how good it is at so if, for example, if you have a network and you know what part of the network you don't observe, and you try to fit your model, try to learn the parameters, and you get some results, and you would like to have some measure of how good it is, what you can do is you can actually take the same network, even the same unobserved elements, because In the end, it will also depend on which part is unobserved. Here, it was all randomized and averaged over multiple realization, blah, blah, blah. But if you have a particular case, you can, like take the same network, take the unobserved part, then do simulation yourself and see how good is actually your reconstruction. And this will give you even maybe some number on like how big is the error, most likely, right? Which can also be useful in this case.
Okay. Okay, great. Thank you very much. And any other questions? If not so far, then we can move on to the second discussion, a second part of the talk.
Cool.
Maybe.
Okay, so I think I probably didn't do the best job since there were no questions. Sorry for that. But you can also look at the paper and you can contact me if the subject itself is interesting. I'd be happy to tell you more. Or you can even look at the GitHub, because I also put some examples there, and this could also be maybe pedagogical to look at it. So yeah. So sorry. Maybe the second part will be more digestible, let's say. So the second part I call challenges and how can they help in solving new problems, which will relate to something that one of the answers that I gave to Hanlin before. So I already kind of told you that loops are a problem, right? They are a problem because our inference method is basically written for trees. So once you introduce loops, it's no longer an exact method, it's just an upper bound. And depending on how many loops and the structure of the loops, this upper bound may be is sometimes very good, but sometimes it may not be so good. So we actually wanted to test it because it actually depends on many factors, not just the loops, but also the original parameters and so on and so forth. So we took the worst possible case. We took the square lattice, which has like exponential number of loops. It's horrible for using BP in general, not only DMP, but BP in general. And this is what we noticed. So we still have some recovery power here, right? This is the error on the parameters. But you can see that there's a certain gap, which is significant. It's more than 10%. Funny enough, like even if you introduce unobserved parts, it seems like you probably converge to a very similar solution. But there's a gap, so probably it's an incorrect solution. It's correlated, and we can actually see it. So this is one of the solutions that you can reach. So it's correlated, it's nice, but you can see that there's a bias. You basically get bigger alphas, which probably compensates in a way this problem of DMP being an upper bound now. Okay, so you can always use it. You can have this error. It's okay. But the question is, why do we really want to learn those parameters in the first place, right? So you have some data, you work on COVID, let's say, you get plenty of data. There was like really a lot of data on COVID. And what do you want to answer? What do you want to do? Why do you want to learn the model? You typically want to learn the model, right? But why do you want to do it? Well, you want to do it because you want to do some prediction in the end, right? Either you want to do some scenario testing, or you want to say like, oh, in the next week there will be 1 million cases or whatever. But in the end, what you're really interested, whatever your task is the prediction part. So what have we been doing for now? We had some data. We used this learning procedure to learn the model, but then we wanted to do prediction. And for prediction, you can do simulation. You can do Monte Carlo, as we already said. But sometimes you prefer to use the inference methods of your choice. Like in our case, DMP is an inference method of our choice. Why would you want to do it? Well, in our case, DMP is basically extremely fast. So if I want to test 1,000 scenarios, it's much more useful than just doing Monte Carlo for thousands of millions of times. But there may also be other reasons for that. Sometimes maybe simulation is even a bigger problem. But the main thing is that we care about prediction. And in this, if we only care about prediction, there's a thing that in machine learning is called the effective model. Effective model is the case where you have some model which you know is incorrect, which by the way is almost always the case for epidemic spreading. So you know that the model is incorrect, but it has some prediction power. So in our case, even if we assume that the model is correct, we actually don't care about finding the correct alphas in the end. We care about being able to do prediction. And now we made an observation. Okay, so we said like, all right, we're still fixed to this square lattice. We want to challenge this difficult case, this case that our algorithm have problems with. And we have this interesting observation. So we do the learning procedure. We already know that we learn incorrect parameters of the model, okay? But how good is this model in prediction? So what we did is like, we took this incorrect model. This might be slightly surprising, but we took this incorrect model and we tried to first do prediction with those with this incorrect model using our DMP inference procedure. And then we took the real parameters and we did the same, which is we tried to do prediction with our inference method. Okay. And it turned out that those incorrect alphas, those here, are actually better in prediction than using the true ones. Now you may think like, wait, that's impossible. Well, the key here is that for prediction, we use DMP, right? So we didn't do simulation. Obviously, if we do simulation with correct ones, we would get correct results. But we assume that we need to use our inference methods for some reason, because it's fast, because it's, I don't know, better in some cases, whatever. But the observation is that actually our learning procedure, what it was doing, it was not trying to find better correct alphas. It was trying to find better alphas, the alphas that would give you better prediction. I know the prediction is still not great. It's like the error is like around 20%. But this already gave us a hint that, wait, so our procedure is actually looking for an effective model, not the true model. So maybe we can use it because we care about prediction. We want to predict the spreading, the future spreading or whatever. We don't care so much about the alphas themselves. We don't want to do anything with them. We want to use them for prediction. So maybe just by observing this plot, we can think of something better, like what would be the typical case that you would do in machine learning? So you would try to increase the expressibility of your model. So first of all, we decided that look at it slightly different. So what we did in the beginning was that we have some data, we used some procedure to find the true model, and then we used the true model, or at least we thought the true model, with our approximation inference method to find prediction. But what we noticed is that in this case, it's better to actually do it consistently. So we do the learning using the same inference method, which we exactly do, our DMP, and then we use it for inference, use the same inference method for prediction. And we notice that this is better, okay? But it's still not good. We still want to do better. So what would you typically do in machine learning? So you would try to, for example, increase the expressibility of your model, right? In a way, this is what the deep neural nets are doing, right? We introduce more parameters. We hope that the expressibility of the model will be better. So currently, our starting point was that we have those alpha ij parameters, and we want to find those pi marginals. So how would you increase the expressibility? Well, you can introduce more parameters. In our case, parameters are basically connected to edges. So our first idea was to, let's add some extra edges, right? I mean, we don't care about the network being correct. We don't care about the alphas being correct, but we care about our model being able to express more possible values of those marginals, hoping that at some point it will just fit perfectly to the marginals that are coming from the data. And this was a disaster, actually, in the end. So we tried that. But it turned out that we have those alphas here that are the true ones, and we have some extra alphas here, which should improve our model capability of getting the correct marginals. But it turned out that our model, what it's doing is just zeroing out all the other edges. And it's doing it extremely well. So you actually can have even much smaller samples, which will not give you a very good estimation of alphas, but it will still zero out the extra alphas. We were, I mean, now when I think about it, it's maybe not so surprising, but at that point we were like, hey, maybe, okay, it doesn't solve the main problem, but maybe it will solve a different problem. So maybe it will solve a problem which is also very important in the network community, which is the network reconstruction problem. So maybe we can actually use our algorithm to reconstruct network structure, not just the parameters. And this is where we are going back to what Han-Lin was asking about, right? So we did this extra experiment before even this whole business of like full network. We wanted to check, okay, so we know that it's very good at it, but how does that depend on the loops again, right? We know that loops are not good for us. And then it turned out that actually reconstruction part can be extremely good even if you have a lot of loops. So we did this experiment. We took our favorite square lattice again here. And then in the actually in just the learning part, what we did, we add those extra edges. So those dashed lines are extra edges. Our algorithm thought that the full network is the one with like the dashed ones and the whole ones. And we wanted to check whether it will be able to zero out all of them, despite this network having even more loops than the square lattice. And we already know that our algorithm is not very good with square lattice. And it turned out that it's extremely good. I mean, obviously, if you observe the whole network, you can always use maximum likelihood. But even if you don't use it, our method just destroys this network reconstruction problem. Even if you have 25% of unobserved nodes, we're still almost perfect. I mean, basically, it's perfect reconstruction. You need to have like 50% of unobserved nodes to see that actually, well, now your reconstruction is not perfect. It's still not awful. It's like 80% for the rock curve surface. But I mean, 50% is really a lot. Not observing half of the network is a huge problem. And you can still do reasonable reconstruction. So that was a shock for us. And that led us to this part that I already presented, which is that you can actually use our method for reconstruction just by doing thresholding, because our method is extremely good at just zeroing out those edges that are simply not there in the original dynamics. But the problem still persists, right? Okay, so it's nice. We got a new element for our algorithm, which is useful. But we still want to do something in this case of like reconstructing, learning the parameters, or actually in the case of prediction, right? In this case, what can we do if we know that we're not good at reconstructing parameters, but we care about prediction? We know that just adding edges is not a good idea because it will just zero it out. So we decided, okay, we can do something else to increase the expressibility, but not adding new edges. Again, we have our starting point is the parameters alphas and marginals p. But now what we introduced, we basically take our network and we copy it. Okay, so we have two separate networks, which are exactly the same, but those two networks can have different set of parameters. And as a result, in the DMP procedure, they will also may give different marginals. And now our objective will not just be marginals, but this will be an average over marginals. And this can obviously be done in multiple ways. You can have average, you can have max, mean, whatever. It turned out that actually just taking an average is already very successful. So now, to be more precise, I have some data about spreading, okay? I have two networks, and I simultaneously learn those parameters on both of those networks according to marginals, okay, of the observed spreading. But I don't compare like those marginals with the spreading, but I compare this average. And this way, I hope that the average will have a bigger expressibility than just learning a single network. This is a very, I would call, a machine learning approach, but it actually works. So here's the actual likelihood. So now, instead of having just marginals here, I have the average of marginal. So now this scale divergence is not between those marginals, but between the marginals coming from the data and the average of the marginals of those separate, let's say, network models. And this actually worked. It wasn't able to zero out those edges anymore. But what it's able to do is now you introduce more and more of those extra, you can call it a mixture model or like replica model, or maybe a multi-layer network in a way. You can think about it this way as well. And the more you introduce them, the lower the error. And most importantly, it also works in the unobserved regime, which is important for us, right? Because otherwise you can always use, again, maximum likelihood. And obviously this increase your numerical part because you have more and more parameters, but you can find a sweet spot and a reasonable error that you could accept at some point. So this was our like an effective model approach, which also in the end turned out successful. But on the way, we also solved other problems that we are not even trying to solve in a way. So that was very, very useful. And that's all from me on that part. And, thank you very much. I hope it was at least a bit useful. And yeah, thank you for having me.
Thank you so much for this nice presentation. And I myself learned quite a lot from this talk, although previously I did have some experience working on dynamic message passing approach, but still it's very nice. Thank you very much.
Thanks.
So now if there's any question related to the first part or second part, feel free to unmute yourself and we can have a short discussion maybe. So if not yet, may I ask one more question or two?
Sure.
Let me forgot what I'm trying. Yes. So like when you say you use the data and to use the data to optimize or to infer this parameters or do the prediction, if the data is like generated by this dynamic message passing approach, or how do you obtain this data?
I'm puzzled about. I mean, data can be generated by the model, right? DMP is just an inference method, so you don't use it to generate data.
Okay.
Right? You generate the. I mean, I was here only using IC model, so I took a network, I generate the data, then I, for example, hide part of the network, get rid of the structure, and then use this with DMP and this whole learning procedure.
Okay, so
sorry if I misunderstood your question.
No. I was wondering that because you say in some sense, although we cannot perfectly recover this parameter alpha in the spreading process, but we can do better prediction even we don't have this perfect parameters. I'm wondering why we can do that.
Okay.
If the actual dynamic is happened in the way like it happened with this parameter, and why we can recover a better result without this essential information, I would say.
Yeah. So when I say prediction, what I precisely mean is that like my algorithm. So my learning algorithm give me some parameters alphas, right?
Yeah.
Whether it's a mixture or not, they just give me. So they give me a model. And now I can plug this model into DMP, go back, right? And say, what is the marginal probability at some point in the future, right?
Yes.
But I can also compare this marginal probability with the true marginal probability. Now, what is the true marginal probability? The true marginal probability is that I take the original model that I used to generate the data, okay? And I can use Monte Carlo to compute the true margin. I mean, I use quote unquote because this is still simulation, but this is I mean, the longer you do the simulation, the closer you'll be to the original margin. So I did like million Monte Carlo runs to approximate them. So then I do the comparison between the marginals that I get from DMP with the model I learned, whether it's a good model or effective model or just straightforward wrong model. with the true marginals which I got from the original model that I used to generate the data. Sorry, it was a bit convoluted, but I hope I answered.
Okay. Okay. So my question, I was thinking is
there's data that I use for there's data that I use for learning. Okay, there's data that I use for learning.
Yeah.
But this data was generated with some model, and I know this model because I did the simulation.
Yeah.
And I can use this model to generate on the side much more data to get the true values of the marginals.
Yes.
And now the question is, like, I have this set of data, I learned something from this set of data, and whether what I learned gives me the marginals that are, how close they are to those true marginals, right? So this original data may be because I think I understand your question is probably that I already have this data, so I know the marginals, but that's not true, right? You have some data that you can use to, let's say, compute the marginals, but they will be very far from the true ones because you have, I don't know, like 100 cascades, 1000 cascades. But to have a good plus also, your data may be limited to like 5 time steps, but DMP is not limited. Once you have the model, I can tell you what happens in 10 time steps, 20 time steps, and so on and so forth. So the comparison is made separately on the data that I generate with the original model, but like I generate like, you know, like millions of cascades so that I'm sure that I'm close to the true marginals. But the original data may be crappy, right?
Okay.
For example, maybe the best example is that like the original data may be missing information about a certain node. So I have no idea. I cannot use this data to recover this marginal, but I can use it to learn the model, then use DMP to find the marginals on this unobserved part, and I can still compare it with the original model, right?
Okay.
Which the original data would not give me any information. So maybe that should answer.
Okay, now I have a better understanding.
So there are like two separate data streams. Sorry, actually, your question was good. At the beginning is
okay. Yeah, it makes sense. Thank you very much. And by the way, I do like the the idea of converting this inference problem, inference is a parameter to the network reconstruction. It's quite like a smart way that you convert your difficulty but into some opportunities, kind of.
Yeah. That is actually a funny story because we send this paper to ICML, and in ICML, once you get a review, you have only 1 week to answer. Wow. And it was like a crazy week. It was a crazy week, and we tried because they had some good points, but also quite demanding. So we had to do a lot of experiments. And this is actually how we found out about this record. It was not the part of the paper, but it was kind of part of the answer. And then we were like, wow, this is actually pretty useful. We'll do another paper on that. So that's useful. So I see that probably my talk was a bit too technical, so maybe to make it less useless for you guys, I can, since this is about giving hints to young scientists, I consider myself still relatively young. but maybe one hint, one thing that I would tell myself when I was a couple years younger is that now I really understand because you're at the stage when you finish your PhD, you want to apply for postdoc, you want to apply for grants, right? There's a lot of these competitions that you will probably take part in to get some money, to get a position, and so on and so forth. And my short experience already showed me that this is extremely random process. You may think that you had the best possible project, and this may be true, and you may still not get the offer, the money, whatever, or you may think that your project is crappy, which probably it's not, and you can still be surprised that you get the money, the offer. So remember, it's super random, and what's the lesson coming from it? And I will give you a great example, which happened to me actually, so that I'm not just throwing words. But the lesson from that is that, first of all, don't worry. If you didn't get it, don't worry. It means nothing. Continue trying. And second of all, keep trying, basically. That's don't worry and keep trying. And I will give you an awesome example. Like I've sent this grant to European Union 4 years ago. I thought that the grant is great. I don't go into details which calls and so on, but it's reasonably prestigious grant. I got a review, which were quite positive, actually. It was nice. Good reviews, but still below the threshold, which is extremely high. And I was like, okay, cool. We didn't get it, but we got good reviews. So we resent the grant. We took into account all of the comments of the reviewers. We did a lot of work. We also did a lot of work in the first stage. It was actually a lot of work. And we resent it again. And I chatted with my friend, who's here also in Los Alamos, a great scientist, who also sent the same grant in a different discipline, but exactly the same European grant. And he had the same situation. He sent the grant. He got a very positive reviews. So he resent it. And then what happened to both of us was, again, the same. It was in a different part of career. He did it already in the past, but it was the same story. Our second round of reviews were extremely negative. I was basically that close to be below the threshold of not being able to reapply. And he was in the same situation. Now, what happened is that he said, like, okay, I don't care. I have a position here. It's all good. I'm not sending this. This is a lot of work. I'm not doing it anymore. And I wanted to do exactly the same. And the mentor that I've sent the grant with said, no. It's a good grant. Let's send it again. And I was so frustrated that I've sent exactly the same grant. I did no changes. Literally, I only changed the parts that changed in the code, like the names of some of the sections. It was the same text. I didn't even answer any reviewer's comments because I thought they are bogus. And I got the grant with like super high reviews, exactly the same grant. It's like no difference. And I was like, like above the super high threshold and almost below the super low threshold. So this is a real story. And yeah, so don't worry about it. It's super random, but also keep trying. I mean, obviously it needs to have certain quality. I'm not saying just sending random words of like deep learning generated grants, but although this may also work actually, but still don't do it. But yeah, so maybe this piece of advice to save my today's talk. Thank you guys again for having me. And
thank you for sharing this kind of painful experience. But I'm glad finally you success.
Yeah.
So anyone else want to say something? Otherwise, maybe we can finish our session today because the time has already passed a little bit over the 1 hour time. So thank you again very much. Thank you very much again, to be here. And I really enjoyed the talk. Hopefully we can meet maybe or collaborate in the future.
Sure. Thank you,
Great.
guys. Bye-bye.
Thank you very much. Bye.